Good evening. Hi. Welcome to the session. First off, I want to thank you guys all for coming out here. I know these are long days at the conference, and it's the last session, and we've got this party at Universal Studios afterwards, so thank you very much for showing up. I appreciate it. My name's Jonathan Kellio. I work on the Common Language Runtime, and we give sessions like this one at pretty much every conference we go to. Under the hood sessions that don't introduce any new technology, that don't give any tips or tricks, that don't talk about best practices, no how-tos, nothing like that. In fact, that don't talk about anything that you actually really need to know in order to be successful writing applications for Longhorn or for whatever environment that we're talking about. And we do this because we've listened to you and we know that you guys are techies. You like to hear about interesting technical details of the technology that you use every day. On that theme, what we're going to talk about today is we're going to focus on some new WIDBE features that I think most of you, if not all of you, will be using almost every day. And those two features are edit and continue and generics. So you've probably seen this slide a few hundred times already this week. It's the WinFX namespace slide. Because what we're talking about is down in the CLR, there is no single box that I can point to on this slide and say, this is what we're talking about. Because generics and edit and continue actually apply to just about every box on this slide. Because I couldn't use this fancy high-budget overview slide, I had to make up my own much more low-budget big picture slide for the purposes of this talk. For what we care about, here's what the world looks like. At the top, you have the IDE, Visual Studio, within which you have your editor, where you work on your source files. Those run into the compiler, spits out some IL in the executable, and that runs with WinFX on top of the CLR. And though all of my demos are going to take place within Visual Studio, what we'll be talking about, what we'll be focusing on, is what happens inside the CLR to make those demos happen. So first up, generics. Generics is not a new concept. It's been in several languages for many years. Many of you in this room are probably familiar with the concept of templates in C++. Very briefly, templates are often used for collection classes, like, for instance, a stack, that you want to work with multiple different data types. You write your stack with a type parameter, usually people just use T, that takes the place of the various types you might end up using in your stack. And then as you use it, you instantiate it for whatever you want to use it for. A stack of integers here, a stack of doubles here, a stack of points over here. And the C++ compiler does some magic for you and actually writes custom code for each one of those instantiations of a stack. In the .NET world, with generics, they look very similar from the user's perspective. You write your stack with your type parameter. As you use the stack, you instantiate it for different types, int, double, point. But your language, whether it be VB or C# or C++, doesn't actually do the magic for you. Because the IL that those compilers will generate is itself generic. We save the tricks for the JIT compiler and the runtime itself. So that's enough talking. Let's go take a look at a demo of how this stuff works. So what I've done is I've written a generic stack class, just as we were talking about before. I've put my type parameter T on the class. We'll overview real quick how this thing works. It has an array of T's that we're going to use for the elements that are on the stack. It has an integer that keeps track of the current depth of the stack. The constructor allocates the array to an initial size and sets the depth to 0. A pop function figures out where in that array the top of the stack is, saves the element that was at that position, then actually does the popping of the element. This thing here, t.default, this is something you only see with generics. It means use the default value for this type, which for an integer would be 0, but for an object would be null. That line is just there to tell the garbage collector for object versions of this that the stack no longer cares about this object because it's been popped off. The push function checks if the array is full. If so, it enlarges it, and then pushes the new element onto the array. For the purposes of this demo, there's really no reason to look at enlarge array. Just suffice to say it makes the array bigger. My demo function, very simple console application. Within a loop, it pulls some lines of text from the console, parses those texts, those lines into integers, pushes them on the stack, and then runs back through, popping them off and printing them out. So it just reverses our list of integers that we type in. Just briefly to prove that this works, 1, 2, 3, 4, 5, and indeed they are reversed. So now what we'll do is we'll look at the IL and the metadata for this generic stack. This is ILDASM, the IL disassembler. If you're familiar with ILDASM, you'll notice a few things are different about generics right away. At the very beginning, the line that defines the generic stack class contains some information inside of angle brackets. And that information is the type parameter, t, on the class, and the constraint on that type parameter. In this case, mscorelib system.object. That means that any type you use for t must derive from system.object. That's fairly easy to do, since everything derives from system.object. As you look farther down, you start to notice a bunch of exclamation point 0 or bang 0 notations throughout the ILDASM display. That refers to a type parameter. Bang 0 means look at type parameter number 0 for this type, or t. So we look at the array field, and it says this is an array of bang zeros. Bang 0, or this is an array of type t. Now we're going to go look at some IL for the pop function. ILDASM has this nice feature where it will show me the source lines of C# that correspond to each IL instruction. So I'll turn that on, and I'll open up the pop function. So now we can see which lines of IL implement each line of the C#. And we'll look at the instructions that implement this one line. This was the line that stored the element from the top of the stack in a local variable before returning it back from the pop function. That single line of C# expands to 5 IL instructions, which we will look at coming back to the slides, how those get executed. So the IL virtual execution system is a stack-based machine. That means that every instruction in IL takes its arguments off of something called the evaluation stack and pushes its results back onto that evaluation stack. So if you wanted to add 3 and 4, you would push 3 onto the stack, push 4 onto the stack, call the add function, which would pop those 2 off, and it would push back on the result 7. In this case, our first instruction is load arg0. This loads the 0th argument, or the this pointer for one of these methods, onto the stack. The next instruction is load field. That pops off a pointer to an object from the evaluation stack and pushes on one of its fields. In this case, the array field. So we watch it, and it pops off this and pushes on this.array. The next instruction, load local 0, loads the local variable at index 0 onto the stack. In this case, that was the variable that we used to store where the top of our generic stack was. The next instruction, load elem, this is a new instruction for generics. What it does is it pops off an array and an index into that array, and it pushes back on the element at that index. I say this was new for generics because in the pre-generic world, we had a different load elem instruction for every different type of array you might have had. You had load elem.i4 for integers, load elem.ref for object arrays, etc. In this one, the load elem instruction takes a bang 0 to say load elem of our generic type. So that pops off what we have on the stack, and it pushes on the appropriate element of the array. The final instruction, store local 1, pops one thing off of the stack and puts that into local variable number 1, which was where we were storing our ret val. So we'll come back to ILDASM, and now we're going to use it to look at metadata using a tool called metainfo. Metadata is arranged in tables. Metainfo is a nice tool that can interpret those tables and show you the semantics. Here are the types that were defined. Here are the methods that were on those types. That's all very nice, but we actually want to see what those tables look like. So we put it into raw mode, and then we go show it. Metainfo is kind enough to tell us what the tables look like, what their columns are, and that sort. We're going to focus first on the typedef table, table number 2. This table tells us which types were defined in our module. And the type that we're going to be interested in is the one in row number 2. So we'll look at these columns. Column 0 is flags. That stores things about a type, like whether it can be inherited from, whether it's abstract, those sorts of things. Column number 1 is the name. And we see here that it says string number 1b. That's an index into the string heap. The string heap contains all the strings that are used elsewhere in metadata. What we'll do is we'll pull up another ILDASM and another metainfo, and this time we'll tell it to show us the heaps so that we can look at what's on the string heap. Bring this over to the side here. I will pull up the other metainfo. Excuse me for a moment here. There we go. And we can scan down to see string number 1b is the name generic stack. This was the name of our type. Column number 2 stores the namespace of the type, which coming back we see was string number 28, or a generics demo. These next 3 columns, extends, field list, and method list, in the metainfo display contain metadata tokens. The way you read a metadata token is you look at the first 1 or 2 digits, that tells you the table you're looking at, and the last 6 digits tell you the row. So for the field list column, which is column number 4, that shows us where the first field of this type lives in metadata. In this case, table 4, column 1. So we can scroll down to table 4, and again we find some flags on the field, and we find its name. We can go back and look on the other metainfo at string number 4e, and that shows us that we're looking at our array field, and then a signature which says blob number 1f. Coming back to our other heaps, we see that what that is a binary blob expressed as hexadecimal bytes. We'll talk later about what signatures are and how you read them, but for now that's what we'll say about them. So I could go through and continue showing all of this within metainfo and following the tables like this, but that rapidly gets to be hard to keep in your head. So we'll come back to slides and we'll show it in pictures. So we looked at the typedef table first, and we looked at the generic stack. We found that string in the string heap. And then we followed the field list pointer down to the field table, where we pulled out the name and the signature of each field. If we'd continued on in metainfo, we could have followed the method list pointer to the method table, which contains, among some other things, the names and signatures of all of the methods. And then from the parameter list, or the param list column of the method table, we can find out where the parameters are of each of these methods. So if we follow param list for the constructor, we find that the first parameter is initial size. The parameters then follow consecutively until the first parameter of the next function. So you can see that constructor has just the initial size parameter. If we then looked at pop, we would think that its parameter was toPush. Well, it's not, because that doesn't make any sense to have a pop function with a toPush parameter. And you can tell that by looking at where the param list for the push method points. We see that pop and the following method push both point to the same location. That means that the first method, pop, has no parameters, and the second one, push, has that parameter toPush. You can also tell that by looking at the signatures, but this is kind of a quick way to see that. If we look at the metadata as it is now, it's very similar to what the metadata would be like for a non-generic stack. As it happens, the signatures, which we'll mention soon, will tell you that it's generic, but other than that, it looks very similar. So there are two other tables that make it a bit more obvious. The first of those is the generic param table. It contains the list of all generic type parameters that are used by any type in this module. It has an owner field, which is another metadata token pointing back to the type that uses this parameter. In this case, it points back to generic stack. The name field tells us the name of the type parameter, T, and the number field tells us the number of that type parameter for the given type. The last table we'll look at is the generic param constraint table. This contains the constraints on each generic parameter. Again, an owner column points back to the generic parameter that uses each constraint, and then the constraint tells you which types are legal to pass as this parameter. Coming back to what we saw with ILDASM, for this type T, we can use anything that derives from system.object. So I promised earlier that we would look at signatures and see how to decode these things. To pick an example, I'll just pick the one that looks longest and most complicated, the push. In order to read signatures, you need some tables and you need some grammars. And those are available in a number of different sources, including the Common Language Infrastructure spec and several books. One that you may not know about, just came out this week, is the Common Language Infrastructure Annotated Standard. This has all of the CLI actually in print instead of in Word documents, and annotated for some of the more hard to understand sections. That's actually available from the Addison Wesley folks here. So when you look in one of these references, you find that the first byte of every signature is something called the calling convention. That tells us what kind of signature we're dealing with. You look up that value in a table, and you find that calling convention to 0 means instance method, or a method that has a this pointer. Now that we know it's a method signature, we can look at the signature grammar to understand that the calling convention is followed by a number of parameters, a return type, and then mini-signatures for the types of each parameter. We can drill in. Number of parameters is fairly easy to read. It's just 1. The return type, again, it's a table lookup. You find that return type 1 is void return, or returns nothing. And then each parameter type is a parameter signature. And if we look at the grammars, the parameter signatures always start with an element type. Again, this is another table lookup. But the interesting thing about this one is you look for number 1-3 in any of these tables, you won't find it in any of the published tables. That's because it's brand new for generics. When you see a type signature with element type 1-3, that means the type is a generic type parameter. And the following and the number of that type parameter will follow. So in this case, it's telling us that the type of parameter number 1 is generic type parameter 0 for our class. That was T for generic stack, so this tells us parameter 1 is of type T. So we look back at what we've got. We have an instance method with one parameter, void return. The parameter 1 was of type T. We can look back in the metadata, and we know that its name was push, and the parameter's name was toPush. And we can translate all that back into C#, and we come up with void push type T, toPush. So I mentioned earlier that the JIT compiler now does all of the magic that the C++ compiler would do for templates. We can see that by playing around with it in the debugger here. Here we create a generic stack of integers. And what I'm going to do is I'm going to step into the constructor, and then I'm going to disassemble it and look at what comes out. I'm sorry, I couldn't figure out how to make the disassembly get bigger, but we don't actually have to look at the disassembly for this. Basically, all we need to know is that the disassembly for the constructor on the integer version of generic stack is pretty close to one screen in size. That's about all we need to know for this. So we'll step back out. We'll go now to the constructor for the object version. We'll step into that. We'll disassemble it. And you notice right away that it's significantly longer than the integer version was. By the way, all of this is debuggable code, so if you're in the front row and you can read it and you think it's nasty, that's why. The optimized code is much better. If we step back out and we look at the one for form, the generic stack instantiated for a form type, we disassemble it. Well, it's still pretty long. It looks like it might about be the same length as the one for object. Well, if we come back to the command prompt here, what I've done offline is I've just copied and pasted the disassembly for those different constructors out to text files. And we can compare, using FC, the constructor for the generic stack of objects with the constructor for the generic stack of forms. And we find out that not only did they look about the same length, those two constructors had exactly the same JITted code. The reason for that was that the JIT compiler knew that an object and a form were represented pretty much the same in memory. They're just 4-byte pointers, or 8 bytes on 64-bit, out to an object on the garbage collected heap. And since the generic type constraint just required an object, it didn't care whether it was a form or not, the JIT knew that it could use the same code for a stack of objects as it could for a stack of forms. To see that a little bit more in detail, come back to slides. When I initially created the stack of integers, you got an object out on the GC heap for that stack. It had an array of integers, and it also had a hidden field that pointed to something called a method table. The method table is an internal CLR data structure that is one per class, and it holds, among other things, pointers to the JITted code for the methods of that class. So as you go on using it and things get JITted, those pointers get updated to include more and more members of the class. In this case, for stack of int, as the program ran on, it would have pointers to the x86 or IA64 or whatever your platform was, code for the constructor and pop and push specialized for int. When we created one for objects, again, it looked fairly similar. It had its array. This time it was an array of objects instead of an array of integers. It had a method table pointer pointing to the method table for stack of object. And as we saw, that had different code. So it pointed off to different x86 code that implemented the stack functions for object. When we created a stack of forms, again, it had its own array of forms this time. It had the method table for stack of form. The trick here is that the method table for stack of form points to the very same JITted code that the stack of object did. So not only is the code identical in terms of comparison, it is actually the same code. So that's generics. Coming back to the big picture slide, we're going to talk about edit and continue next. Edit and continue will bring in the debugger a little bit more. And you'll find actually that there's a lot that's going on inside of all of Visual Studio, inside of the editor, inside of the compiler, inside of the debugger, to make your edits take place. I'll give you a little bit of an idea of what that is, but I'm going to focus mostly on what's happening in the CLR, because there's plenty of stuff to talk about there as well. So we'll jump right into a demo and go edit a method. Again, we have a console application, fairly simple. This one also has a loop that pulls numbers off the console. This time it adds those numbers into an array list. And then at the bottom of the function calls print statistics, which in turn computes the sum of those numbers and then prints it out to the console. And then there's a console readline call to make sure our window stays around. We put a breakpoint on console readline. We're going to come back in and add the ability to compute an average. So I'm going to go ahead and put in some numbers, 3, 4, 5, 6. We see that it came up with the sum of 18, so I can add. That's good. We'll come back here, and now we're going to modify print statistics while we're stopped in it to compute an average. So we add a new local variable for it. We add a line to compute the average. We add another line to print it out. And then again, I just put a read line at the end so that our console window stays around. We keep running. And it says the average is 4.5. So what happened? Behind the scenes, to make that happen, when we said go after making that edit, Visual Basic, through the debugger, sent down to the runtime something called delta IL and delta metadata that described what we had done in that edit. We're going to take a look at what delta metadata looks like. This is actually the one part of the demo you can't go do at home. Delta metadata is particularly hard to get at, so I cheated and used an internal test tool that we have to pull out the delta metadata for this particular edit. Delta metadata is arranged just like the full metadata. It has tables. But we'll notice as we look down that a lot of these tables are empty. The typedef table doesn't have anything in it in the delta metadata. Why? Because we didn't add any new types. In fact, you can't add any new types, but we didn't add or change any definitions of any types. Similarly, the field table doesn't have any fields in it because we didn't add any new fields in this edit. The interesting table is the method table, which does have one row because we changed one method. Come back to slides here and show how this delta metadata comes in to the process and works. At the time that we were stopped at that breakpoint, in the process itself, we had the full IL and the full metadata for the program as it was originally compiled. The method table has a column that we haven't previously mentioned, the RVA column. RVA stands for Relative Virtual Address. It's an offset from the base of the loaded module to, in this case, where the IL of a method is loaded. So for the second row of the method table, we see the RVA 20A8 for the print statistics function, and we can follow that to figure out where the IL for print statistics is. This will become important in a minute. When the debugger, or Visual Basic through the debugger, provides us with delta metadata, it also had a method table, as we saw, and that method table had one row. It also provided us with delta IL. Delta IL actually contains the complete IL for just the functions that changed. So it's kind of a coarse-grained delta. And the RVA in the method table of the delta metadata is a relative virtual address into the delta IL that tells us where the new code for print statistics is. Now, in order to apply the edit, we have to do two things. First, we have to get the code into the process from the debugger. And you'd like to be able to put the code immediately after the original IL for the module, because that would be nice and clean. But we can't, because the original module is hemmed in by other data. We might have loaded one module after the other, after the other, after the other, so they're all just packed in there, and we can't move them around. So we just have to find some place elsewhere to put the delta IL in. Next we have to inform the runtime which function this delta IL is for. To us, it's pretty obvious. We have one print statistics function over in the delta metadata. We have one print statistics function over in the full metadata. Ergo, they must be the same one. But you could imagine that we had several print statistics functions in the full metadata, and that we had changed more than one of them with the delta metadata, and we need to figure out which one mapped up with which one. So there are two tables that are specific to edit and continue in the delta metadata that help us do this. One of those is the ENC log. It records all of the changes to metadata that have to occur to make our edit take place. It has two columns, token and function code. The token is the metadata token in the full metadata of the row that was touched by the edit. And the function code tells us how that row was touched. Function code 0 means that it was simply replaced with the row from the delta metadata. But we still don't know. So we know from just looking at the ENC log that table 6, row 2, in the full metadata is going to be replaced by something, but we don't know by what yet. That's where the final table, ENC map, comes in. The ENC map table maps from rows in the delta metadata to rows in the full metadata. It has a single column called token. You might wonder how a table with one column can map from something to something else. The way it does that is that the from information is implicit in the ordering of the ENC map table. So as we scan the ENC map table, we see that the first token we come to is table 6, row 2. And we say, oh, that's the first table 6 token we've come to. Therefore, the from must be the first row of table 6 in the delta. And then the target row is easy to figure out because the token says it directly. It says table 6, row 2 in the full metadata. So that tells us where the new IL for print statistics is and which print statistics it's for. We then copy the row over into the full metadata while updating the various CLR data structures that keep track of where the IL for each individual method is. As it happens, since we just copy the row, the RVA in the metadata becomes invalid. But that's okay because we did update the other data structures that care about that. So that's all well and good. We've told it where the new IL is, and the JIT knows to go JIT it the next time it gets called, but we were actually inside the method when we edited it. That means there's actually machine state out there that we have to fix up so that we can switch over and actually run the new code. Here's what it looked like. At the breakpoint, the IL virtual execution system was stopped right before a call to console.readline, because we'd stopped it on that breakpoint. It had local variables and arguments, and it had an empty evaluation stack. That corresponded to a certain state in the x86 machine itself. We were stopped at an x86 call instruction, and our arguments and locals had been distributed across registers and the stack as the JIT saw fit to do so. Then Visual Basic provided us with new IL for this method, and it said, please replace the IL with this new stuff. I've colored the changes in a different color on this slide, but that's just for our convenience. The runtime itself just sees a huge block of IL that's going to replace the old stuff. So what the runtime does when it gets this new IL is it sets breakpoints at strategic locations throughout the original IL. Those locations are all the places where the evaluation stack, the IL evaluation stack, is empty, like it was the beginning to the call of console readline. Those breakpoints also appear in the original x86. And once they're set, the runtime continues running until it hits the next one. In this case, that's immediately, because we were actually stopped at a 0 stack point. At this point, the runtime comes back and asks Visual Basic, I'm at this call to console readline in the original code. Where do I need to move to in the new code so that it will behave like the user would expect? When we changed the function, we actually added another call to console readline at the end of it. So in our delta IL, we have 2 calls to console readline. And remember, though I've highlighted them in red, the runtime doesn't see that highlighting. It has no idea whether the first call or the second call to console readline is the new one. So it asks Visual Basic to help. And VB's been watching, and it knows that you put a new console readline at the end of the function, and it knows that the console readline in the original IL corresponds to the first one in the new IL. So it tells us to move there. At that point, as far as VB is concerned, we extend the local variables to include the new one for average. Again, we have to go into the x86 to actually apply this, because so far we've just been talking about a virtual execution system. The way that works is the new IL gets JIT compiled. We then move the IP from the old code to the new code, and then we extend the stack to contain the newest local variable. At this point, our edit is complete, and this function is running in the new code. The old code, of course, is still around, and the breakpoints are actually still in the old code. So if that method was running on multiple threads, or multiple times on the same thread, the next time it hit one of those remap breakpoints on another thread, this same thing would take place again to remap it in all the places where it was being used at the time. Let's throw a wrinkle into it. Let's say that instead of stopping at a breakpoint before console readline, we had actually stepped into console readline, had it blocked, waiting for us to enter something at the console, and then it hit the pause button in the debugger and come back to print statistics and made our change then. The only difference that you see in Visual Studio is that your call stack has console readline on it. The call to console readline has a green triangle instead of a yellow arrow next to it. But in the processor, in the x86, it's very different. We actually have the local variables on our stack pinned down by the local variables for console readline. So we can't extend the stack to put our new locals there because there's already something important there. So when Visual Basic gives us the IL, this is where those remap breakpoints really come in. When we continue running from console readline in this particular case, the remap breakpoint won't be hit until we return from console readline. It'll fire on the first instruction, or the first 0 stack depth point after the call to console readline. And at that point, we're now back to being the last function on the stack. We have room to expand our stack to contain the new variables. And so the rest of the remap goes pretty much the same as it did before. Visual Basic tells us that we were at the line after the console readline. We JIT the code. We move the IP in the x86. And then we extend the stack, and our edit is done. Now, we potentially ran a lot of code inside of console readline before we finished that remap. And so you could imagine a lot of things taking place there. Let's say that instead of just adding some new lines afterwards, what if we had put a try-catch around that call to console readline while it was executing? And further, let's say it had thrown an exception. If that had happened, the exception would not actually have been caught. You added a new handler around it, but we never got back to one of those remap breakpoints to put the handler into effect. This is one of the caveats with our support for edit and continue, and one of the things that languages will try to make better for their users. So it's for exactly that reason that Visual Basic doesn't let you add a try-catch around an active call, because Visual Basic made the decision that any code that you have on your screen should match what's in the process. And so they detect that situation and prevent that from happening and getting you into that strange situation where you're not exactly sure what's going on. So with ENC, you can also edit a class, adding new fields and such like. We'll come back to do a demo of that. And again, my main program is fairly similar to what it's always been. It takes a bunch of lines from the console in a loop. This time, it's adding those to something called a stat builder, which is a class that I'll show you in just a minute. And then it calls a print statistics function on the stat builder. The stat builder contains an array list as a field, and it contains a sum field that's going to keep track of the sum of it. The add function computes a running sum. As you add each number, it sums it up with the previous numbers. And then the print statistics function just prints out, again, the number of numbers in the list and their sum. What we're going to do again is we're going to modify our stat builder to also compute the maximum and the average number in our list. So we're going to enter 3, 4, 5, 6. We hit a breakpoint, again on a console read line. We'll come back to stat builder. We'll add a couple new fields to the class to hold the average and the maximum. We'll come into the add function. We'll add some code to compute the max. This code just looks at each number and says, is this bigger than the biggest number I've seen so far? Great, that's the maximum. And we add some code to compute the average. And then we come down into print statistics, and we add some code. I don't know what that dialog is. We add some code to actually print the average and the max. Because all of our code actually happens at the time that it got added to the stat builder, we want to make sure that we can add a few more numbers. So we'll sort of force ourselves to come back up to where we're, again, reading numbers from the console. And we'll start running again. So now, what we'll say is we'll add, whoops, I'm going to have to scroll that back up again. We'll add 1 and 2. And we come back, and it says our sum is 21, our average is 3.5, and our max is 2. Well, that's not right. Why did that happen? This is one of those things that you have to be aware of as you're using edit and continue, which is that when we added that code to the add function, it had already been called a bunch of times with the old code for adding the old numbers. And so since our code for computing the maximum basically assumed that it had seen all the numbers as it was getting added, it came up with the wrong answer. That doesn't mean our code was wrong, because if we stop debugging and we start over and we say 3, 4, 5, 6, 1, 2, it gets it right. So that's just one of the little tricky things. So actually, if we again look through my cheating tool at the delta metadata for the edit, we again see a bunch of empty tables. The typedef table still doesn't have anything in it. Now the field table does, has a couple of the new fields that we had added. The method table contains new method entries for the methods that we changed as well. We can come back to slides to look at how this metadata gets applied. Once again, at the time of the stop, we had full metadata for what was originally compiled. The interesting tables here are typedef and field. You can follow the field list, as we did earlier, to see where the first fields, or all the fields, of this type live in the field table. The delta metadata, as we just saw, contains a couple of new fields, and it also contains an ENC log and ENC map table. This time, we see function codes other than 0 in our ENC log. We see function code number 2. Function code number 2 means add a field to a class. And the token in the ENC log tells us which class. So the first line, or the first row of the ENC log table says, add a new field to type number 1, which is our stat builder type. The second line of the ENC log tells us where that field is going to go in the field table. It says we're going to change field number 19. That's way down at the end of the field table. We'll talk about why in just a sec. The third and fourth rows of the ENC log add a second field to the stat builder. And again, those fields come at the end of the field table. The reason for that is that if you tried to expand the field table to make some room for the fields and put them right in a row with the other ones, you would then have to go find every field reference, every reference to a row in the field table, not only in the metadata, but also all through the IL. It would be a huge, huge operation. It would take forever and it'd be really hard to do. But by putting these fields on the end of the field table, we've broken our promise that we were going to put all the fields in order, or all the fields in a row, so that you could look at the first one and then just keep scanning to find all the rest of them. My computer science profs used to always say you can solve any problem in computer science just by adding another level of indirection, and that's what we'll do here. We'll add a new table called field pointer that lists the tokens of our fields in a contiguous order, and then the metadata engine is smart enough that when we point our field list to a field pointer table, it knows that this is going on and it can deal with that extra level of indirection. Now, as before, where we had some state in the virtual execution system that needed to be updated, we still do, because we made these edits to the class after we had instantiated several, or well, one of them in our case, but potentially after we had instantiated several of these classes out on the heap. So what that might have looked like is something like this. You'd have seen the objects out on the heap. They've got their numbers array and their sum field. They've got their method table pointer. And they also have another hidden field called a sync block index. The sync block index tells it where to find a structure called the sync block for each of these objects. Most objects don't have sync blocks. We only create them when we need them for something. In V1, we used to use these for doing the locking on an object. We'd go lock on the sync block. We also hang some other things off of there, and we're now going to use it to hang these extra variables. I suppose you could imagine that we might extend the objects in place. You're probably familiar with what I'm going to say right now from past problems we've had with these things. The objects are actually crammed right up against each other in the heap by the garbage collector. So we'd have to move it around and find a new place for it and expand it and fix up all those pointers. And if we did that for everything at once, that would take forever. So what we do instead is, instead of having the JIT emit a standard field access for each of these fields, we have it emit a function call instead. And that function call goes and looks for a sync block and looks for the fields hanging off of that. So in the case of our demo just now, the first new field that got touched was max. So that function went and looked for a sync block. It didn't find one, so it made one. And then it looked on the sync block and said, do we have a value, or do we have a space for this max variable? We didn't, so it made one. And it initialized it to 0. I've put the value 8 in here because, well, it's just a value. When you later touched the average field, it did the same thing, and it appended the average field onto the linked list. In this way, we just add the fields as we need them to each individual object. So as you've seen, the runtime's support for edit and continue is extremely powerful. you can do all kinds of things. You can completely replace a method body. You can add new local variables to it. You can add a method to a class. You can add a field to a class. You can't do any of that with a generic class, but you can do that with everything else. And we saw some examples of where all that power, if you exposed it directly, would lead to something that was pretty much unusable. So it's left to the languages to decide what edits they want to expose to their users. We already mentioned the case of exceptions and remapping, where Visual Basic decided not to allow you to add a new exception handler when you're around an active call. But there are some other things that languages need to do in order to make things make sense to the user. One thing is the compiler needs to be careful about how it generates code. If your compiler is too clever and it keeps things on the IL evaluation stack for long periods of time across a bunch of statements and a bunch of IL instructions, then it spreads out the zero stack depth points. And that means that more code is going to run before you can remap. So that makes it a little harder for you to get your edits applied. Another interesting case is that many edits will have a cascading effect. So imagine that you had a global function called foo. And in your class, you have a lot of code that references foo. Then you go and you edit your class, and you add a new private function called foo. Well, now, instead of just adding new IL for this new private function and being done with it, you now have to go find every place inside your class that used to call the public function foo, the global one, and change that to call the local private one on your class. So instead of just sending one function, you find yourself sending several functions, replacement IL. So this brings me to a shameless plug. We are having tomorrow a language implementers lunch outside of this room in the Tools and Languages track lounge. If you are a language implementer, someone who is creating a .NET language or already have a .NET language, it's mostly a social event. But if you want to talk about what it takes to extend a language to be a .NET language, or what it takes to implement generics or edit and continue, come on down to that lunch. It's tomorrow at 11:30 in the Tools and Languages lounge. Oh, there's my shameless plug. So that's pretty much it for this talk today. I'd like to ask everybody to please send feedback up on ComNet. This has been my first PDC talk, so I'm especially keen to hear what you guys have to say. Thank you very much for coming. Enjoy the party, and I'll be staying around for questions. So coming up to the microphones if you have questions.
So how much work is it for a language to do edit and continue, i.e., why is it not in C#?
Why is it not in C#? So the question is, how much work is it for a language to do edit and continue? So you got a little bit of an idea of that from this talk. The language needs to be able to keep track of how your edit is going, where it happened. The compiler needs to be able to generate code that is edit and continue friendly. You have some of those problems of what sort of experience you want to give to your users, what sort of edits you want to allow, whether something is going to be allowed or not, and how you detect that. And then just the generation and the dealing with the delta IL and delta metadata. So in the case of C#, with all of the other features that were going on, generics and things like that, edit and continue was a whole lot of work to do in addition.
Is there an API that a language adheres to be able to do, answer these questions and events and?
Sure. So there is a standard API at the CLR level that is the debugging API. That's the API that does all of this communication for asking the debugger and through it the language where it needs to move, where it needs to remap, and what's going on there. Plus, the metadata APIs are how you actually generate the delta metadata. So if a language hooks in, or if an IDE hooks into those things, then that's how it works.
Yeah, about the backup. I'm assuming that backup, the is the semantics of the backup, a pure change of instruction position. There's no attempt to undo state.
Absolutely, that's correct. The question was when we moved the arrow back up to the previous, back up into the earlier loop to do another console read line. The question was, did we try to do any kind of going back in time? Did we try to unwind any state? And the answer to that was, well, no, we didn't. We simply moved the instruction pointer there and started running as if you had just done a go-to to that particular line.
And when you're talking about the edit and continue work in the JIT, you mentioned some concerns that sounded very processor-specific. And I'm wondering if you have any comments about how portable the edit and continue work in the JIT is for other processors.
I see. So the question is how everything that I talked about today was for x86, and how portable is edit and continue to other processors. So edit and continue is today only available on x86. That doesn't mean it is not possible for 64-bit platforms, but as you've seen, it's a fairly large effort to get it going on x86 to begin with. I don't know of any reason it could not be done on 64-bit under the current high-level architecture. It may not look exactly the same as what we've shown today, but I think it could be done.
Thanks.
Hi. I know metadata architecture and the framework, but to protect intellectual property, like somebody who has access to ILDASM can just, look at my source code and then, get a whole lot of information. And what if I wanted, turn off that feature? Is there any way to do that at all?
So the question is, can you metadata, while it helps us as the CLR do a lot of cool things, it also helps developers very easily disassemble your code with ILDASM, dig through it, figure out what it does, and the question is, how do you protect your intellectual property in a world where you can do that? So there's always a roaring debate about this every time it comes up. You can't turn off metadata. It really is. It is required. It has to be there. But there are various tools available that let you obfuscate the metadata and the IL as well. These things do all kinds of fancy things like changing your names that have meaning to garbage. Sometimes they do other tricks to make it difficult to use ILDASM to disassemble your code. At best, though, an obfuscator can only make it about as hard as it was for unmanaged code. And while that was hard, somebody who was determined to figure out what your code does would be able to dig in there and do it. It might take them a little bit longer. They might have to know more about how the processor worked and that sort of thing, but they could do it. Same goes with obfuscated code. They can figure that out if they try hard enough. So if your intellectual property for a particular thing is so sensitive that you really don't want anybody to be able to find out about it, the only real way to protect yourself there is to never actually ship the code. Distribute it as a web service, say, and let people get at it that way.
Cool. Thanks.
How is the whole edit and continue stuff dealing with code access security? Especially, it seems you can inject code to strongly named assemblies and stuff like that through the debugger.
So the question is, how does edit and continue interact with our security system? So in order to use edit and continue, there's a couple of answers to this. So the code will continue to run under the security restrictions that it was set up with. So through edit and continue, if you edit something that's in partial trust, that will continue to run in partial trust. As far as worrying about, or as far as the fact that you can actually change code in a process, in order to use edit and continue, you have to be debugging the process. And once you're debugging the process, you own it. You can execute any code you want in that process already without even using something as fancy as edit and continue. So in that way, it doesn't actually add any new ways of doing bad things with a debugger. So the security there comes from the fact that you have to have certain levels of permissions to debug something.
One question.
Any others?
Hello.
Where are we at?
So all the
Go ahead.
new tables you have mentioned, they are just in the memory, right? They are never written into the assembly.
So the new tables, edit and continue does not persist those new tables out to disk. There are ways that you can use the metadata APIs. I'm sorry. So the new tables, like the ENC log and ENC map, is that what you mean?
Right.
Okay, yeah.
And even the interaction, field interaction.
Right. So the question is, the new tables for edit and continue, like the ENC log and the ENC map, and the indirection tables, like the field pointer table, do those ever show up in an assembly on disk? For the ENC log and ENC map, they will only show up on disk if you save your delta to disk for some reason, which Visual Studio does not do. For the field pointer and other such tables, those can show up to disk if you use the metadata APIs in a certain way. But that is to say, if you don't do compression of the APIs, or if you don't do compression of the tables at the end. But commonly with at least the Microsoft languages, I don't believe those will ever show up to disk. Certainly not in the edit and continue scenario, because the edit is actually applied only in memory, and then you never actually persist back out to disk. You get the changes out to disk the next time you do a full build of the project.
Thank you.
Yep. Next.
Instantiating, and you're instantiating that template with the parameter that's a reference type. So in those cases, my question is, it seems like you're going to lose some opportunities for inlining in those kinds of scenarios, because if you were to actually inline the code, you would no longer have the ability to use it for any given reference type, right?
Okay.
So, are you understanding my question?
I am understanding your question. Yep.
So in those situations, will the jitter inline the code and have two versions, or just have one version but no inlining?
You know, to be perfectly honest, so the question is, in the case of reference types for generics where we're sharing the code under the jitter, will the jitter inline those? Will the jitter inline those things, or will it prefer to keep the particular shared thing? And the answer to that is, I honestly don't know.
Okay.
There might be some other folks from the CLR in the room who might know that, but I don't know that question.
My other question was just, okay, so you created a generic stack template, and then you instantiated it with an integer. And we saw that the generic stack class had an entry in the typedef table of the metadata. Does the generic stack for int have an entry in the typedef table of the metadata?
So the question is, we saw that the generic stack class that I created itself had an entry in the typedef table. When you instantiate that for int, does generic stack of int have an entry in the typedef table? The answer to that is no. The way a generic stack of int works is, when you use that, there's a special kind of signature that gets used to say, I want a generic stack of integers. And that gets linked to, I believe, the typespec table, where you can, and that shows the ones that actually get instantiated. But there is no typedef token for each individual instantiation of a generic type. It's just a signature that describes what it is.
Okay, so in that case, it seems to me that in at least prior versions of the CLR, if you define a type and have it inherit from another type, somewhere in the metadata you got to provide the typedef token of the class you're deriving from.
That's correct.
So that means that you cannot derive from generic stack of int.
That's not so, because what we've done, so in the metadata, the place where, sorry, repeat the question. The question is, given that, how do you inherit from an instantiated generic type? So if there is no typedef token for generic stack of int, how do you create a class that inherits from that? So the way inheritance works in the metadata is there's a field that I sort of skipped over in the typedef table that is extends. And that is, in previous versions, a typedef or typeref to tell you which type you're extending from. In WDBI with generics, you can also put a type spec token there, and you can say, I want to extend from generic stack of int in that way.
And that's all that the type spec table is used for, is just for instantiated template classes?
It is not. It is also used for other things. I don't have an example ready off the top of my head.
Thank you.
Any others?
Is this stuff all being submitted to ECMA and ISO? And that's the first question.
The question is this all being submitted to ECMA and ISO? Probably. We haven't figured out exactly yet.
And the second question was, is there some way in the IDE or in the command line for the languages to say, I want to generate an ISO or ECMA a CLI compliant image?
I don't know for sure. The question is there a way to generate a CLI compliant image?
Like, do you understand the concept of CLI compliance?
Absolutely, yes. So the question is, do we have a way of generating a CLI or CLS compliant image from each individual language? As of v1.1, we did not. As of WDBI, I do not know. Any others?
Good presentation, by the way.
Thank you.
In the edit and go thing, if I add some code before the IP, and say and I added an optional parameter to the function, would the CLR still handle it?
So the question was, if you add some code before the IP and you add an optional parameter to the function, will the CLR still handle it? So I'm going to split that into two questions. One, you can totally add code before the IP. That's okay. It probably won't run unless you drag the IP back up and make it run.
In cases of, say it's a recursive function.
If it's a recursive function, it will definitely run on the next call.
Okay.
The optional parameter question, can you add an optional parameter? That's actually not allowed. You're not allowed to change the signature of the method. You're only, at the CLR level, you're only ever allowed to either replace the body or add a new method to the class. So you can't actually extend the parameter signature of a given method. You can perhaps play some compiler trickery to get close, but you can't actually do that.
Thanks.
Yep. Any others? Okay. Thanks, everybody.